Hi, welcome to my poster. My poster is about mass accommodation and viscosity of secondary organic aerosols from explicit modeling of gas phase oxidation. I'm Manabu Shiraiwa from University of California, Irvine, and here is my co-authors on this poster. So the topic of this poster is about mass accommodation coefficient, which is an essential parameter for modeling of SOA partitioning and chemistry. And to describe this process, mass accommodation coefficient is the most widely used parameter, which specifies the probability upon the collision of molecules to the surface, how much fraction of them can be incorporated into the particle phase. But this parameter is often applied without specifying if and how deep a molecule has to penetrate under the surface to be regarded as incorporated into the condensed phase. This aspect may not be really critical for liquid particles because bulk diffusion is so quick, but if particles adopt viscous semi-solid or gaseous solid particle phase state, then this how much distance molecule needs to be traveled down to the bulk to be effectively incorporated, this aspect may become critical. So to address this issue, we introduce effective mass accommodation coefficient, alpha effective, accounting for the influence of volatility, diffusivity, and particle phase reaction as described in this equation. And the effective mass accommodation coefficient based on this very paper that we can calculate what would be the effective penetration depths for molecule to be incorporated into the particle phase. The derivation of this equation, you can find it in this publication. So this parameter is useful because it can be implemented into the Hooke-Suttergin gas phase diffusion correction. So if you want to simulate the SOA partitioning kinetics, for the viscous particle phase state, one might need a really sophisticated model such as mosaic or KM gap. But even a simple approach using this alpha effective into Hooke-Suttergin approach, then you can actually effectively consider the bulk diffusion effects. So this shows a non-reactive partitioning case as a function of time, and then here is a mass concentration in the particle phase calculated with KM gap as a benchmark, and also the mosaic model, and also with a number of Hooke-Suttergin approach with a different alpha. You can take a look. Often the case that alpha is assumed to be 1, and then this one is a case for semi-solid particles with bulk diffusion coefficient of 10 to minus 15 square centimeter second minus 1. If you use alpha equal 1, you overestimate the SOA growth. But then KM gap and mosaic, which is consistent with this black line and red line, and this line with Hooke-Suttergin approach of alpha effective, you can actually capture, there's a deviation at the earlier stage, but then you can capture the equilibration timescale really well with Hooke-Suttergin approach with alpha effective. This case shows with reactive cases that there may be some particle phase reactions, and that can be also addressed using alpha effective, that with the simulation that KM gap and mosaic and Hooke-Suttergin with alpha effective all matching really well. Whereas if you use alpha equal 1, that would not simulate the kinetics well. So alpha effective depends on volatility and bulk diffusivity. This figure shows how alpha effective would change depending on the volatility and phase state and bulk diffusivity. So alpha is often 1, and that's a case for different volatility compounds. But then for semi-volatile compounds and intermediate volatility compounds, if the particle adopts semi-solid, that alpha effective can go down. As you can see in this figure, alpha effective can significantly deviate from 1, and it can go as low as 10 to minus 3, 10 to minus 4. For low volatility compounds, alpha effective would stay 1, even particle becomes semi-solid or even glassy, because that it's low volatile enough, so anyway it stick on the surface. But you would expect this impact for semi-volatile compounds, and that's actually observed by in Liu et al. By Jose Jimenez group in 2019, that they measure the mass accommodation coefficient as a function of C star, and then they see the reduction of alpha for condensing onto alpha pining SOA, and actually our theoretical prediction can capture that well, assuming that alpha pining SOA would be semi-solid. So this concept seems to be working well in terms of simulation and also matching with experiments. And for other issues, we developed a tool that we can simulate SOA viscosity from explicit modeling of gas phase oxidation using the Gecko-A model. So we have a parameterizations to predict the glass solution temperature of SOA compounds, and we implement that to Gecko-A, which generates millions of oxidation products and partitioning. So this figure shows that viscosity measured by a number of studies for alpha pining SOA as a function of relative humidity, and we simulated each of the studies conditions, SOA formation conditions, using Gecko-A, and then predict the viscosity of SOA through the prediction of glass solution temperature. As you can see, the model can predict viscosity relatively well, but actually underestimate by a few orders of magnitude. And this may be because that Gecko-A does not consider auto-oxidation and particle phase chemistry. So to fully reconcile this experiment and model, it may be necessary to include these missing processes in the model. But nevertheless, the model can do a very good job in predicting the viscosity, at least a trend, and also so relatively capturing well the experiments. And we can incorporate this alpha effective approach into Gecko-A, because traditionally Gecko-A use either instantaneous partitioning or using alpha equal 1. But we can incorporate this alpha effective approach by considering the effects of particle phase state, and we compare that for two studies with Lemba, Wolf, and Kidd et al. And we see that alpha effective could make a big difference, as you can see in this blue line, that if the particle phase becomes really glassy, then that would suppress the condensation of semi-volatile compounds. It doesn't suppress the condensation of low volatility compounds or extremely low volatile compounds, but it could suppress for the condensation of semi-volatiles, and that could lead to the difference in the particle resulting particle viscosity. So with that, conclusion is alpha effective provides an efficient and easy way of accounting for the influence of volatility, diffusivity, and particle phase reactions. So if you apply alpha effective in Hooke-Suttinger approach, then you may not need the sophisticated model, but you can effectively consider these effects. So that would be useful for application in air quality models. And we implemented viscosity predictions into explicit gas phase chemistry model, which is a very useful tool for analysis of interplay of gas phase reactions, particle chemical composition, and SOA phase state. And my group is planning to further develop this tool and possibly combining Gecko-A and KM gap model with a reduction of a chemical mechanism, applying the machine learning approach. Yeah, thanks for visiting my poster.